Hello, Gordon.
Hello. Hello.
Let's see.
Okay. Hey, Dr. Shudish, I was just looking through my emails. I tried to send the instructor evaluation form. Apparently it never sent though. I had the email typed out to everybody. I'm not sure what happened, but I'll send it right now again.
Okay. Okay.
I was just checking to
Yeah.
make sure I'd actually sent it before I asked everybody if they'd seen it, but apparently it never sent. So I'm not sure why that happened.
Sure. Yeah. Okay. Yeah. There's. Yeah. It just has to be done in a. Yeah. I think.
Right,
Let's
yeah,
say
yeah.
Friday or something.
Yeah, that's totally fine.
Thanks.
No problem. Just make sure it
Yeah.
sends.
Doing it as a favor, so you can take it back.
It was. Yeah, I'm not sure why it sent though, or why it didn't send though. So I'll get it.
Okay. So we have the final exam. On Monday, the first exam, I suppose, on Monday. Okay, oh, no, not the first exam, sorry. It's 2:45. Did anyone confirm this? So now it's too late, so people have the exam, that unless it's clashing for someone else. So. Okay, so yeah, we will have this online. And it will be up sometime by the morning, so updated by morning. Updated by morning. And due by, let's say, evening, so maximum 11 o'clock, so due by. Sometime before morning, it should be available. And just make it due by 11 by night. Yep. So you guys have been good about that. But the exam is expected to be during 2 hours. So the best is that you pick it at that time and do it. But if you want, you can do it earlier, later, of course. make it suitable. Okay. Any questions on that?
Yeah, just to make sure it's going to be posted on Monday morning.
Yes, before Monday morning. Let us say before Monday 10 o'clock, right? Something
Okay.
like that, right? Okay.
Okay.
Okay. Most probably before that, but just I'm just putting a time there. Okay.
Okay.
I would be surprised by Sunday if you check, you might see the exam. Okay, good. And grading wise, I've been little, usually on a normal semester, I'm caught up with grading, but this is a little, I'm behind on that, but maybe in a day or two, I intend to finish off all the grading. So you should have those, something to work with for that. Okay, any other questions?
So I'm noticing that I have 5 emails in my outbox right now that all never sent. So I'm not sure why. I just tried to send it again and it's also in my outbox. So I'll figure out what's going on with my email and make sure everybody gets the instructor forms.
Okay. Okay. Yeah, that's regarding the evaluation Christian is talking about that I mentioned in the previous class. So he will send you the evaluation form as a scanned copy, and then you fill it in. You will have to actually take a printout, fill it in again, scan it and send it back to him. And he will probably collect it and give it to the physics office. And thanks for doing that. Yeah. So it helps. Yeah. Okay. We were doing radiation. First, we talked about how much average power is going into a particular solid angle. That's called the angular distribution of radiation. How much radiation is going in a particular angle. And we also talked about how much frequency is going in a particular solid angle. So now we have a frequency distribution and an angular distribution of the radiation. And we want to do a little more fine tuning on that expression for the spectral distribution or the frequency distribution so that we can actually analyze a particular problem on Friday. So let's talk about spectral distribution further today. So this is spectral or frequency distribution. Of radiation. Just to give a sort of summary, if we are in position and time, what we said earlier was that the magnetic field, notice the position and time dependence here. So that's equal to minus of mu naught c over 4 pi. This has a nice feature that this has the dimensions of resistance. In fact, this is exactly equal to 30 ohms, right? This quantity in parentheses is exactly 30 ohms. So it's very intriguing idea that what is that physically represent? It's something, a property of vacuum if you want, but surely not the resistance of a vacuum because vacuum has infinite resistance. They're not talking about resistance of vacuum. This is R hat, and as 1 over R, representing the fact that it's a radiation field, and R hat crossed with, let's call it an effective current. So I'm just calling it. And R hat, meaning that it is only theta and phi dependent, and it is retarded. Where the effective current, due to all the charges or currents, is you integrate over the whole space using the variable r prime and find out where the charges are accelerating. That's given by d by dt of the current density is equivalent to acceleration because current density is proportional to velocity. Right? It's R prime and T minus R over C plus R hat R prime over C. So there is this convolution here that R prime is here and R prime is there. So there is an effect from the retardation that contributes to radiation. This is all in time domain. Even though I said spectral distribution, I'm going to write that very soon. And we have electric field is immediately given out of the magnetic field. So it's minus R hat crossed with the magnetic field. And it's also good to realize that magnetic field can also be got out of the electric field. Right? So this forms three orthogonal vectors, the vector R hat, which is the direction of propagation if you're observing it at a certain point, and the electric and magnetic field are perpendicular to that R hat direction. So that's your radiation fields in the time domain. It's also good to point out that the energy per unit time, so I can write that as per unit time, per unit solid angle, is equal to, and that is a nice way of writing this. So this is mu naught C over 4 pi, that's resistance again. This has the dimensions of power on the left hand side, energy over time. And so if this is resistance, that should be current on this side. And it is good to realize that this is equal to magnetic field divided by whatever that coefficient was there in front. So this is mu naught C over 4 pi, and that is 1 over R. So if you divide out this whole thing and take a magnitude square of it, which is, if you notice, if I were to pull out this whole quantity, there is just R crossed with the current coming in. So this is actually equal to mu naught C over 4 pi times R hat crossed with this effective current. Notice this is an effective current. I'm having a vector associated with it. So it is an effective current, which is basically a whole integral. And so that's, and let me also point out this is time dependent. T minus R over C squared. So eventually it is just the effective current that contributes to the radiation per unit energy radiated per unit solid angle per unit time. That's a summary of what we did last week. And in the last class, we got these expressions, at least the version for the first three equations in the frequency domain, and we want to do the fourth equation today. So in frequency domain, the same idea goes through. We calculated instead of time, we talk about frequency. And I should clarify or point out that the moment you go to frequency domain, the magnetic field does not have the same dimensions as Tesla. For example, just to point out, B, let's say R comma T, when I say square bracket, this means dimension of the quantity, right? That's the notation you use in introductory level of physics. This is equal to Tesla. If you want to say units, is Tesla. But if I want B of R omega, which is a frequency, magnetic field as a function of frequency, then notice this is got by integrating over time, and then there is an exponential of I omega t, and that is the magnetic field in the time domain. Exponential does not have any units. Exponential usually spits out a number associated with it, but this is in Tesla and this is in time. So the dimension of magnetic field in the frequency domain is Tesla times second, right? The dimension of time also comes in. So be aware of that, and whenever you're writing equations, whenever you want to check things out, you want to be careful about this fact that the dimensions are changed of every quantity by, by the time, right? Similarly, if you go from the frequency to the time, the units change. With that caution, let me proceed and write down what we derived for the expression for the magnetic field, radiation field, magnetic field in the frequency domain. This comes out to be very similar to what we did earlier, except now the time dependence will change. So this is still 1 over r dependence is there, and we have r hat crossed with, instead of talking about the effective current in the time domain, we now talk about the frequency domain. So that's the only change. This frequency has come in, but I had to specify what is the effective current in the frequency domain. And we don't have to do any integral anymore. That was the nice feature. This comes out to be e raised to I k r, and r is still the same distance of the observation point from the source, and k here is a vector. So k is omega over c in the direction of r hat. Otherwise, I haven't specified k there clearly. So it's in the direction of r hat, but omega and c comes in, which is a frequency. So if I just write k, what I mean is it's a magnitude of this. So that's omega over c. That's a definition. And rest of it is the same. So it is minus ik. So instead of a time derivative, there is a minus I omega that comes in. Always the time derivative gets replaced with minus I omega. And then there is a c, which lets me write it as minus ik. And j itself is now in the frequency domain. In fact, it is even the position is in the Fourier space. So that's k and omega. Notice the point here, I have not only gone to the frequency space for the current density, even the position has been Fourier transformed. Fourier transform the position of the current density and replace it with k, like the wave number, if you want. The best part is no integral needed. Everything is done. It's just a product, right? Multiplication and so. But of course, to get this frequency dependence, you need to have that integral. Anyway, that is a popular statement that radiation is governed by the reciprocal space, or what is called the Fourier space. Once you know the Fourier transform of a current density or the charge density, then you immediately know what's the radiation going to be equal to. As far as electric field goes, in the frequency domain, it is simply got from the magnetic field in the frequency domain. And the earlier expression remains the same. R omega is equal to r hat crossed with e r omega. So that's the main idea is that the magnetic field in the frequency domain is got using this effective current, which is basically the Fourier transform of the current density. What we would like to do now is that we would like to ask what is the energy per unit frequency, not in time, per unit frequency. Earlier we had time, but now we do frequency per unit solid angle. So energy per unit solid angle per unit frequency, how much is that? Right? Earlier we talked about per unit time and then we averaged over time, but this time how much frequency? For example, if you have a cell phone signal antenna, which frequency do you want to send it, and how much of that goes in a particular solid angle. So you would like to have a control on that, and that's what we want to calculate. So we will start from the time domain expression and basically switch over to the frequency domain. That's what we want to do today. Okay. So let's go back and write our energy expression in time domain. So that's time e omega is equal to, I can cancel out some of the mu naughts and so on and rewrite it later on in the same manner. One of the mu naught over c goes away. The 4 pi, actually I should change, there's a small error in what I wrote. Right. And what I wrote here, I think it's visible. Oops. Yeah, here there should be an extra 4 pi, right? 1 over 4 pi, which is a normalization of the solid angle. So that should also be there, and the same thing on the second equation. So add this 4 pi in there. I haven't written this for the frequency domain, so that error did not slip in there. Okay, so going back in here, so this is 4 pi cancel out, there is an r square, and there is the mu naught, that is all. Right, so this is r square times divided by mu naught times c times magnetic field, r comma t, c times magnetic field dotted with c times b r comma t. That's what it is if I were not to write it in the way I wrote it, so that I can identify the effective current. So that's slightly easier. And if you want, I can actually even take the C out, but C has been going with magnetic field all through, so let's keep it. That's your energy per unit solid per unit and time. Let me, since anyway this is a real quantity, whenever I measure the magnetic field at position or at time t, it's a real quantity, I can make it a star. Right? It is never going to be complex. Magnetic field in the time domain is real by construction. But that's not the case in frequency. Whenever you take the Fourier transform, because of that exponential of I omega t, it doesn't have to be real. Frequency components can be complex. So now we want to go to the frequency domain. So what I do is, first I do the integral. So I do the integral in time. So what remains on the left is the energy per unit solid angle. And I'm going to integrate with respect to time. That's minus infinity to plus infinity dt of whatever is there. There are two pieces. It's r comma t star dotted with c times b r comma t without the complex conjugate. And the trick that I'm using here is valid for any Fourier transform of a bilinear construction. The bilinear means there are two functions evaluated at a certain time. And this, whatever I'm going to get here, so I'll start from an integral of two quantities in the time domain, and I will eventually get something in the frequency domain. And this is called the Plancher problem in mathematics. Plancher, I think a Plancher form. But it's a straightforward derivation, you'll see. We have the function here as a function of time. Let's put in the Fourier components of that. mu naught times c minus infinity plus infinity dt. Maybe let me take more space here. So this is equal to half square over mu naught c minus infinity to plus infinity dt. And each of this is a Fourier transform. So remember the Fourier transform formula is d omega over 2 pi. And since we're doing this in time, this is minus I omega t times c times b or omega now. Right? We've gone to the frequency. And we want to take the complex conjugate of this. And multiply the whole thing again and dot product of these vectors. So a lot of things happening simultaneously here. It's a formal expression. Minus and c times. But notice this is an integral in omega, so I should try to put omega prime, right? I cannot repeat omega, the integral variable again. So I write omega prime and r of omega prime. So I substituted the Fourier transform. Now let me manipulate the integrals. The time integral comes only in the exponential, and that's an easy integral to evaluate. Let's do that. So this is equal to, is visible? Yes. So just rearranging integral, and then I will do the one of the integrals which will collapse the other integrals. So that's d omega over 2 pi, d omega prime over 2 pi, minus infinity plus infinity. And let me write this as exponential. Of notice, this has to be complex conjugated, exponential. So that makes it a positive there. So that's I t omega minus omega prime. So I collected the two exponentials together. And whatever is remaining, I just have to write it as a complex conjugate. And this is c times b r omega star dotted with c times b or omega prime, and the time integral is remaining. I put that at the end because I can move that all the way. The only time dependency is in the exponentials. Oh, I should have written that here, right? Oops, sorry. I should have moved the time integral all the way to the right. Let me rewrite this. Sorry about that. So this is c times b r omega star dotted with c times b r omega prime, and the exponential, I write it after the time integral. So this is dt exponential of I t omega minus omega prime. Again, just rearranging the terms so that I can do the integrals in different order. So here, d omega has been collected, integrals c times b and exponentials out here. This integral is very easy, but if you were to naively evaluate this, that will give you an infinity, right? Exponential, and then how does an exponential evaluate at infinity? Those are oscillatory integrals, so that doesn't evaluate, but that's a delta function. So that's exactly a delta function which you can check if omega is equal to omega prime, then that's a 0 in the power of the exponential. That goes to 1, and then there's an infinity remaining. But if it's not 0, then this is an oscillatory integral, so it will average out to 0. So in general, this is actually a delta function. This whole thing is 2 pi times delta function. So if you use that property of delta function, let me move the camera. Oh, I did move the camera already. So that's r squared mu naught and c. Let me write this once. so that it's clear. Again, this has nothing to do with electromagnetism alone. This is a general theorem when you go from an integral in time to integral in frequency of any product of two functions. C times B or omega prime, and that is 2 pi times delta function of omega minus omega prime. I just substituted it, I rewrote it in a sense. But now I can do one of these integrals omega prime because I know how to do delta function integrals. Just replace omega prime with omega everywhere. That's all that is happening. And the 2 pi conveniently cancels out the integral of that. So this is equal to r square over mu naught c times minus infinity to plus infinity d omega over 2 pi of magnetic field r comma omega star dotted with. That's it. So that's the Planck formula. Let me write the first expression right again here so that it's clear what we are saying. So this is what we said is that we started with a time integral, an integral in time of two quantities, bilinear construction, you will say. And I don't have to write star there, right? In the real space. So a bilinear construction in the time space, integral of that. So if you had to integrate the whole function from one end to the other, that's exactly the same as if you're integrating in the frequency, except that the function also has to be in the frequency. So that's a theorem in a sense, and this plays an important role in quantum mechanics where the Heisenberg uncertainty relation comes, where whether you're in position or momentum, you cannot do much because it's a mathematically that the average has to be the same. Average means if you collect all the time information of the function and all the frequency information of the function, that has to be the same. Okay, so if we have this quantity, then earlier what we did was, remember what we had here is change how much energy is going into a solid angle. If I start from here, strip off this integral, and you will get the energy per unit angle per unit time. If I were to strip out the frequency integral, I get the energy per unit solid angle per unit frequency. So it's almost right there, and it's just that the magnetic field quantities have changed. So we immediately have that. The answer that we were looking for, the energy per unit frequency per unit solid angle. Remember, frequency goes from minus infinity to plus infinity, so it is kind of doubled because frequency, negative frequency acts very much the same as the positive frequency. But if we keep it, so there's a double counting in that sense. So this is the same as r square over mu naught times c times, so frequency is gone, so there's a 1 over 2 pi that comes extra, and c times b or omega, and instead of writing it as star time complex conjugate times the function, I can just write it's a magnitude square. So it's very much the same, except this extra 2 pi comes up instead of the time integral. Rewrite this as in terms of your mu naught over c. This will give you 1 over 4 pi times, that's the solid angle normalization of the solid angle, mu naught over c over 4 pi, and times I want a current, so there's a 1 over 2 pi extra that comes up, and rest everything is c times b, this time r omega and we want to divide this out by mu naught C over 4 pi times 1 over R again. This whole very exactly similar to the time solid angle per unit time, except that this is now a frequency dependent magnetic field, and there is an extra 2 pi.
Could you scroll down a little bit?
Uh-oh. That's bad. Oh, yeah, I think I did not press.
Thank you.
Yeah. Okay. So let's process this a little bit. Let's go to new board space, and we have again energy per unit solid angle per unit frequency. That's equal to 1 over 4 pi times a resistance, dimension of resistance, and whatever, and there's a factor of 2 pi because that's connected with that d omega, right? And whatever is the magnetic field divided by mu naught over C, that's pretty much R hat crossed with the effective current, but this time in the frequency domain. Square. That's what we have. The effective current is pretty straightforward actually. So let's substitute that in there. Why write it in that form? So we didn't have any integral in this case. So let me just write that. So this is R hat crossed with exponential of IKR, where K is omega over C, remember? And then there was minus IK, which comes from differentiating the current. This is like d by dt because there is an omega there. And the current density, the Fourier transformed current density, both in position and time, and square. That's what it is. But this can be simplified further because there's an exponential which can move around here. And when I square that, the magnitude of it, e raised to IKR magnitude square, is simply e raised to or is equal to e raised to minus IKR times e raised to IKR, which is equal to 1. Right? So that doesn't contribute. So I don't have to keep this because when I square this, this is gone. Similarly, minus I magnitude square is plus I times minus I. That's equal to 1. All the complex conjugation is trivial and it doesn't contribute at all. So it's just K squared that comes in. So this is, and that can come out actually completely. So this is, let me write this as 8 pi square mu naught C over 4 pi times, this is gone, that's a K square. Actually, I want to write this as 4 pi times, this is K square over 2 pi. That's better because these things go with particular integrals. Like when you do a solid angle integral, it's good to keep the 4 pi. That's just for convenience. And this is what is remaining is R hat crossed with the current density. So how do you find the radiation? Take any current density in the position and time domain, Fourier transform it completely. Fourier transform it in the time and the position, you get this J, and plug that in, square that, that's it. That's your radiation. So really reasonably concrete prescription there. There's one more thing we can process this so that we can do, we're preparing for what we will do on Friday. We will actually talk about something going faster than speed of light. That you would say, oh, how is that possible? But you can go faster than speed of light in a medium. You cannot go faster than speed of light in vacuum, but in a medium, light slows down, right? That's refractive index. So maybe what happens if a particle is actually going faster than the speed of sound in that medium? Right? And that would be an interesting thing we'll talk about next class. But before that, we want to prepare that. Prepare for that. So let's process this a little more. Cross product, two cross products actually is the same as the identity is let me say A cross B. A cross B. That's is the same as A dotted with A times B dotted with B, or you interchange them. Square. If there is a complex conjugate, you want to write the complex conjugate. So here we're talking about absolute value, so we want to take care of that absolute value. Okay, so if that is the case, this will be equal to mu naught C over 4 pi square over 2 pi, and this is, there is a r hat square, we don't worry about that, is current that has to be squared, and then when you subtract it, it is r hat dotted with j that comes in. So that's what you have. But what we want to make the observation that this is actually nice. These two terms actually are connected to each other. So let's recall that r hat. So how can we see r hat dotted with j? So let's remember the current conservation equation. So we have in the time domain, the rho RT plus the gradient dotted with the current density, everything in time and position domain. And because current is, charge is conserved, this is equal to 0. If I switch over to the frequency domain and the Fourier transform the position also, remember the prescription is that all the time, derivative with time goes to minus I omega, and all the gradient goes to I times k. So that's the same as minus I omega. Now I had to switch over to frequency and Fourier transform position, like momentum space if you want. And this is plus I k dotted with j k omega. That's still not the same as r hat, but remember that we are evaluating quantities at a very specific k. Our k has a value. Our k is basically omega over c times r hat. So that our current densities are evaluated not at arbitrary k, it is decided by the frequency. So let me write that, so I can write this as an equality now. So that's I omega k omega is equal to I omega over c times r hat dotted with j. And we learned that I goes away, omega goes away, C can be moved to the other hat. So the dot product of the current density in the direction of propagation, if you want, or the direction in which you're observing, is just the charge density. Right? Until now, because it is only the acceleration that was contributing, so it was always the current density that was coming in, but the charge density also shows up in the sense that we are talking about. In the frequency domain, it clearly shows up. Yes, so that's equal to that. So that will be our expression, which we will use next time. It's 4 pi mu naught C over 4 pi times k squared over 2 pi. K is, remember, omega over C, k is omega over C. So this is magnitude of J minus of our hat is nothing C times C squared times rho of K omega. So let me put the C also there. That will be our expression for calculating the energy per unit solid angle per unit frequency. Again, if we know the charge density and the current density in the frequency and Fourier transform position domain, we immediately know that. In the last 5 minutes, let me attempt to, what if a charge was uniformly moving? Right? That's the simplest you can talk about. And we do know that it doesn't radiate. Right? A uniformly moving charge, that means uniform velocity, there is no acceleration, it should not radiate. That's our understanding, that only accelerating charge radiates. So that should not radiate. So how can we see that in this case? How does that function? What's the mathematical, what mathematics stops it from doing that? So let's recall that charge density R comma T is, let's say, R prime, right? Is Q times, so this is just a charge. So it is, let's say it is on the Z axis. So that's X prime equal to 0, Y prime is equal to 0, and it's moving with uniform velocity. So that's Z minus VT prime. So what we're talking about is that along the Z axis, there is a charge Q that's moving with velocity V, uniform velocity V. That's all. And it's not supposed to radiate. And its charge density will be this. If I calculate the current density, it's simply got by multiplying the velocity, right? So it is Q, so it has a Z direction, so Z hat times velocity, and multiply it by rho. It's V is the only thing that comes up, and write down the whole thing, which I will write as this one. Right? So the velocity vector, which is Z times V hat, multiplied by the charge density, gives you current density all the time for a point. We are interested in Fourier transforming. Fourier transform this. So rho of K and omega, right? So we want to Fourier transform this whole quantity. So that's equal to d cube R. So integrate over all space and integrate over all time. That's the way. So this is all space, minus infinity to plus infinity, and exponential of minus I k dotted with R prime. So we are Fourier transforming now. And this is plus I omega t prime, because this is the inverse Fourier transform. And substitute rho of R prime t prime. So what's that equal to? Substitute this, all these integrals are straightforward. X prime, Y prime gets replaced. So let me do this explicitly. So dx prime, dy prime, dz prime, dt prime, right? So this is dt prime. And all this is minus infinity to plus infinity. E raised to minus ikx times x prime minus iky times y prime, expanding this dot product, minus ikz times z prime, and there is a plus I omega t prime, and that is q times delta of x prime, delta of y prime, and delta of z prime minus bt prime. So the three integrals I can do, I do the x, y, and z. When I do the delta function x prime integral, this goes to 0. When I do the y prime integral, this goes to 0. And when I do the z prime gets replaced with bt prime. So this is equal to all three integrals gone. What is remaining is minus infinity to plus infinity dt prime. Oh, am I in the board space? Yes, still there. Okay. Replace this with vt prime. So that's exponential of minus I z prime v t prime plus I omega t prime. And there's a charge q which I can put it in the front. Integral of an exponential of an oscillatory function, exactly like we saw earlier, is basically a delta function. So this is nothing but q times it's an integral in time, so it is actually q times a delta function, 2 pi, times a delta function of, that is omega plus or minus, actually minus z prime dotted with z prime times v. In general, this is actually z, if you want k dotted with velocity, but let's write it in that form. And did I miss anything? Z prime velocity k 1 over time. There's something missing here, right? Dimensionally off. Oh, there's kz, right? I missed the kz there. So there's kz here. There's kz there. That's kz. We will be evaluating our function at, if you allow me 5 more minutes. So we are interested in evaluating our function at k is equal to omega over c times r hat. A special case, so that's your k. I've replaced that k with this. So that's equal to q times 2 pi times the delta function of omega minus, it's moving in the z direction. So this is omega over c again. And z prime, but this time I have to, since we are doing kz, I have to do the, since I'll be observing, notice particle is going this way and we are observing at r hat, which is making an angle that has an angle theta in there. So that's velocity v times cosine theta. And what did I do? I think I messed up somewhere. Oh yeah, this actually z prime got replaced with v. I think so. This was check this. Okay. So notice I wrote a z prime there. Z prime got replaced with vt prime. So it should have been just kz. So there is no z prime after the integral of z. Sorry. So that's kz times v, which is the dot product of k and v. So k is an arbitrary point in the r hat direction and v is in this direction. So this is, there is no z prime. Okay, that's fair. So what we have is q times 2 pi omega times 1 minus b over c times cosine theta. That's your charge density, and your current density will be very similar. And let's ask, When will this contribute? This will never contribute because remember this is a uniformly moving charge. This should not radiate. This will contribute whenever the delta function is contributing. That means whenever the argument is equal to 0, but velocity of a particle is always smaller than velocity of light. So that's less than 1. Cosine theta is always less than 1. So this actually never will become 0. So this never radiates. But we will actually start from this exact form here. We will summarize this again next class and talk about the situation when we are actually not in vacuum. Then it is possible that this will become a refractive index then, right? So it doesn't have to, the particle doesn't have to actually go faster than light. It only has to go faster than speed of light in that medium. So there's a refractive index that will show up. And if that happens, this delta function actually can contribute. And that will be a special kind of radiation, and that is called the Cherenkov radiation, which is like a shock wave. If you have a fighter jet and you are going faster than speed of sound, what happens is that there is a shock wave generated. It is since you are the plane itself, aeroplane itself is going faster than speed of sound. First, it travels ahead, and from the back, it gets come and if it slows down, it will come and get hit by a lot of energy which is traveling at the speed of sound. So that's a similar thing happens in here, and we will talk about that next time. And with that, we will end the semester. So whatever we did at the very end, we will actually recapitulate next time. Thank you for allowing me extra time too.
See you next time.
Sure.
Thanks.